guys, problem week of 5. I'm doing number 1. It's a true or false with justification. So part A asks the linear span of two vectors in the R3 must be a plane through the origin. That's true or false. That is false. Let's consider these two vectors in R3, and since they are collinear, which means basically a set of linear combinations of the other vector, as we can see they're just linear combinations, then that vector can be deleted, say this one, and even if not, and now it's just a line passing through the origin and not the plane. If you delete it or not, it's still a line passing through the origin and not through a plane. Alright, then let's go to B. B asks, every vector space V possesses a unique minimal spanning set. That is also false. If you go ahead and get a set, every vector space has a spanning set, and if they are linearly independent, it's a minimal spanning set. That's what we call them. So if it's already a minimal spanning set, for every space V, if we go ahead and multiply it by a scalar, the whole set, we get another minimal spanning set. Therefore, it's false because the minimal spanning set is not unique. And here's my little example. If I go ahead and multiply this by my C equal to 7, I get that, and it makes that false. All right, now C is the linear span of a set of vectors in a vector space V always forms a subspace of V. And that is true because a linear span has to be just closed under vector addition and closed under vector multiplication, and it also has to be non-empty. Therefore, it's a subspace, and the theorem is in the book. It's also, I believe, on page 278, as well as the proof. All right, and then I have E, and E basically says, oh, actually D, my bad. But I did E first. I'm going to cover E, then D. So E asks if the Wronskian of a set of functions is non-zero at only one point x0 in the interval I, then the set of functions must be linearly independent. And that is true. And the theorem is 4.5.23. The proof is on page 293, and I believe the theorem is also on that page. And so f1, f2, all the way up to fk functions in the C interval. If you do the Wronskian on those functions, it's a non-zero. If it's a non-zero Wronskian as your answer, at some point x0 in the interval I, then your functions are linearly independent in that interval. And then D would be asking if the Wronskian of a set of functions is identically 0 at all points in the interval I. Then the set of functions must be linearly independent. And that is false. It's also on page 294. It's the first box. When you see it, you will see it. So if our Wronskian of f1, f2, all the way up to fk, our functions is equal to 0 for all of our x's in the interval, theorem 4.5.23 gives no information as to the linear independence of any independence of these functions if it's equal to 0. So here's an example. If you take the Wronskian of this, and then we see that it's equal to 0, and therefore there cannot be a conclusion drawn from this theorem, and therefore it's false once again.